Hello students, this is the week 6 video for elementary statistics. We're going to be talking about discrete random variables. Discrete not being able to keep a secret, but discrete meaning individual values that can be counted or enumerated. Let's take a look at the slides. Alright, to try to focus on this question, how can probability be calculated, let's take a look at this guiding question. What's the probability of flipping a coin 10 times and landing on heads 6 times? I'll give you a hint, it's not 6 out of 10. This is what I want you to be thinking about while we talk about discrete random variables. The definition of a random variable is here. It's a numerical measure of the outcome from a probability experiment. So in other words, it's a number that describes what happened when you did something. For example, in the probability experiment rolling a fair die, the possible values of the random variable are 1, 2, 3, 4, 5, or 6. For example, when will my Amazon delivery arrive? There are a lot of different possible values. There's 12 o'clock, noon, 12 o'clock, midnight. There's any time in between. A discrete random variable is a specific type of random variable wherein all of the values that are possible are countable or finite. So in other words, we can say that rolling a fair die only has 6 outcomes. It has 1, 2, 3, 4, 5, 6. You can see the dots here on this number line. There's nothing in between. Like the result of this probability experiment, this outcome, it can't be 5.5. It can't be 3.14159265, etc. Discrete means it is a finite or a countable number of values. So in this example, we were asked to determine whether the random variables were discrete or continuous. In this case, the number of light bulbs that burn out in a room, it's discrete because you can count it, 0 through 10. The number of leaves on a randomly selected oak tree, well, it doesn't seem like you can count them, but they are countable. So it's 0, 1, 2, etc. We also consider the number of grains of sand on a beach to be discrete because you can have 1 grain of sand, 2 grains of sand, a billion, a trillion, but you don't really talk about 1.5. The length of time between calls to 911, however, is continuous because you can say that this call came before that call, but let's say that this call came at 12 midnight. Well, it didn't come exactly at 12 midnight. It came at 12 midnight and 10 seconds, or 12 midnight and 12 seconds and 1 millisecond. It's subdividable. It's not discrete. It's continuous. All right. For example, here, we're asking you to classify the random variables according to whether they're discrete or continuous. Pause the video, try this one out, and then see whether you can figure this out. All right, the number of goals scored in a soccer game, of course, that is discrete. You can score 1 goal or 2 goals, but you can't score 1.5 goals. The number of planets around a star, that's another discrete random variable. You can't have half a planet, probably, unless you count Pluto. Sorry, Pluto, that's messed up. Temperature in Arizona, we call that continuous because you can always measure it to a better degree of accuracy. You could say, degree, that's a good joke there. You could say that it's 70 degrees or 71 degrees, but you could also say it's 70.5 degrees. You could say it's 70.2516 degrees. It's subdividable, so we call that continuous. And again, heights of students in class, we call that continuous. Even though I say, I'm 6 foot and 1 inch tall, right? I would never say 6.17426 inches tall, but you could do that. So it is continuous because it's measurable in that way. For a discrete probability distribution, it takes all of the outcomes of a probability experiment and lists them in addition to listing their probability. So here, the x is the random variable which stands for the value of a die roll, either 1, 2, 3, 4, 5, or 6, and p of x, that is the probability of x. This is not multiplying, this is probability of x. And the probability of getting a 1 is 1 out of 6. Probability of getting a 2 is 1 out of 6, etc. This is a uniform probability distribution, which you should know that term, but it's not necessary to know for the test or the final. Just wanted to let you know that this is uniform. And it's uniform because all of the probabilities are the same. One thing that you should know about probability distributions is that probability distributions follow a couple of rules. They follow this rule, which is that the sum of all the probabilities is equal to 1. And they follow this rule, which is that all of the probabilities are between 0 and 1, which makes sense because a probability is a numerical measure of the likelihood of an event, or of an outcome, I should say, and it is either 0, which is impossible, or 1, which is certain. So some of these discrete probability distributions are legitimate and some are not. Pause the video, try to figure out which ones are good and which ones are bad, and then unpause. All right, you should have identified that these first 2 are good and these ones are not good. Here's why. This one's okay because the values of random variables, they can be negative. It's possible for this value to be -1. The only thing that can't be negative is the probability. So these probabilities are all positive. They're good to go. They add up to 1. 0.2 plus 0.3 plus 0.1 plus 0.4 equals 1.0. So that's good enough. All of these add up to 1, and none of them are negative, so that's good to go. For letter C, though, you can't have negative probabilities, and here's a negative probability. Remember, you are allowed to have a negative value as the value of the random variable as x, but you can't have it as a probability. And here, if you added all these numbers together, you would not get 1.0, you would get 0.97. That's too small. Moving on here. Here's an example which deals with DVDs, which I don't know if students rent DVDs anymore. Usually you just use Netflix or Hulu, or this video not sponsored by Netflix or Hulu. The table shows a probability distribution, which is one of the probability distributions that we talked about here. A probability distribution for the random variable x, where x represents the number of DVDs from a Redbox location during a single visit. Again, this video not sponsored by Redbox. You can see that the number of DVDs is either 0, 1, 2, 3, 4, or 5. That means that when people walk up to this Redbox, they either decide not to rent a DVD, or they rent 1, 2, 3, 4, or 5 DVDs. It doesn't look like anyone has rented 6 DVDs in this example. And all these probabilities represent the likelihood of these outcomes. For example, there's a 6% chance that somebody walks up to the box and says, nah, DVDs are for suckers. And there's a 1% chance that somebody walks up and is like, okay, I want to watch all of the, I don't know, what's a movie series with 5 movies in it? Well, I don't know, but whatever that movie series is going to be pretty long and preponderous, and only 1% of people are going to be bold enough to undertake that adventure. This says there's a 10% chance that people walk away with 3 DVDs, like all 3 of the Star Wars movies, the original series anyway. All right, once you have a probability distribution, you can make what's called a probability histogram. You should remember histograms from our previous discussions of graphing data. A probability histogram is very similar to the histograms that we did before, except this dependent variable here is no longer the frequency. It is now the probability of each value. It's kind of a similar idea, and the x-axis is still going to be that independent variable. In this case, it's the values of that discrete random variable. So for all of these DVDs, we can list the probabilities like this, and we can show that the largest probability is they walk away with 1 DVD, and the smallest probability is they walk away with 5 DVDs, etc. So that's a probability histogram. You might be asked to make one of those. If I was asked to find the mean of a discrete random variable, it's a weighted average. So in other words, it takes into account the likelihood of all the different outcomes. So what we're going to do is basically take all of the all the individual random variables and multiply those random variables by the probability of those variables. Should make sense because I'm looking for the probability of each outcome and how likely that outcome is to occur. I'm going to show you an example here. And examples on the next slide. For example, if I'm asked to find the mean of a DVD rental box like this, I would take all of the different outcomes that are possible and multiply the probability by each outcome. So in this first case, I'm doing 0 times 0.06 because the likelihood of this outcome 0 is 0.06 or 6%. I'm multiplying 1 by 0.58, 2 by 2 or 0.22, I should say. It's fairly straightforward. You just multiply across and add them all together. That's 1.49. So this is the mean of the probability distribution. But what does the mean of the probability distribution mean? Oh my God, I got so many good jokes today. It actually translates out to what's called the expected value. As you could probably guess, the expected value is what we expect to happen. Another way to think of expected value is the average outcome. So for example, as you do more and more experiments, you get an expected value that is more and more similar to the average value. In other words, it's what we expect from the average outcome of one probability experiment. So in this case, that means that the expected value of this random variable is 1.49. Notice that the expected value is exactly the same as the mean value. That's what happens with a probability distribution. The mean value is also known as, it's AKA, the expected value. Here's the interpretation. That means after many rentals, the average number of DVDs rented per person is 1.49. You might say to yourself, well, that doesn't make any sense. You can't possibly walk away from the machine with 1.49 DVDs unless the last person that watched the DVD was a little rude. But it doesn't mean that every time you walk up you get 1.49 DVDs. This is just an average number. We use expected value as an average in order to answer larger questions, like if one rental has an average of 1.49, what would happen if 1,000 people came up to this rental machine and rented DVDs? What would we expect to happen? And then we'd multiply this number by that number of people that came up to the machine. All right, here is a practice problem. It describes a spinner and a devious friend that asks you to play this game. Here's the probability distribution that summarizes the game. If you want, pause the video and take a look at this. Make sure that this makes sense to you before moving on. Keep in mind it has all of the descriptions of the payouts and the sectors here. All right. And for the practice, it does ask for the expected value of the game. And remember that the expected value is the same as the mean value. So that's why we use the probability formula for the mean value. We multiplied all of the random variables, like this -1, times all the probabilities, like this 0.2. We multiplied across and then added them all together. So the expected value is 0.7, which means after you play this game many, many times, the average result after playing the game is winning 70 cents. Oh. Well, that actually sounds like a pretty good game. I mean, as a matter of fact, you can't win 70 cents by getting any of these individual outcomes. However, after you play this game many times, each individual game is going to win you 70 cents. So in the long run, what's going to happen? What if you play this game 100 times? Well, if you play the game 100 times, you can multiply the average result of one game times the number of games that you played. So if you play this game 100 times, you should win $70, which is a pretty good game for you and a pretty bad game for your devious friend. All right, this was a video about week 6, the discrete random variables week. I'm going to record another video shortly that describes the second half of this chapter, which is all about binomial random variables, which is a special subset of the discrete random variables. All right, students, good luck studying.